So number 13, at equilibrium, remember the rate of the forward direction is equal to the rate of the reverse of the direction. So since they're going back and forth at the same rate, there's no change in the concentration or no change in the pressures, letter A. Letter B, at equilibrium, which is true. Well, there's no net change to the system. That's true. At equilibrium, the concentration of the reactants and products stay the same. That is true. The forward and reverse reactions cease to occur. That is not true. They are occurring, but they're occurring at the same rate. And at equilibrium, the rates of the forward and back reactions are identical, and that is exactly what equilibrium is right there. All of those are true. Number 14, write the appropriate equilibrium constant expression, K sub C, for the following reaction. So this would be products right here, and then reactants. And so we do CO2 to the second power divided by reactants, CO to the second power times O2 to the first power. And that would equal K for number 14. Number 14.5, we have write the appropriate equilibrium constant Kc for, and so we'd have the products AB to the second power divided by A to the second power times B to the first power. That would be equal to K for 14.5. In 15, it says consider the following reaction. What is the equilibrium constant expression for the reaction? So watch out for this. This one's a liquid, so it's going to be 1 on the top because that's a constant concentration, divided by H2, and that's going to be to the second power, times O2, and that's going to be to the first power. So this would be the equilibrium concentration constant for it, which is letter D. Number 15, the following gas phase reaction occurs at 500 degrees Celsius. At equilibrium, concentrations reactants are 10, 5, and 10. What is the value of K sub C? So we could write the equilibrium constant as Z over X times Y, and then don't forget to square that one. And so of the reactants and products, so that means 10 is X, 5 must be the Y, so don't forget to square that one, and then 10 must be the Z right up here. So we end up with the 10s canceling, and we have 1 over 25, which ends up being 0.04 for the K value in 15. 15.5 is a similar question, but now we have a little bit different reaction. So we have A2B2 on the top, and then on the bottom we have A to the second power, B to the second power, and it says the concentrations are 1 for A, so 1 squared on the bottom, 2 for B, so 2 squared on the bottom, and 2 for A2B2, but that would be to the first power. So we end up with 2 divided by 4, or 1/2, or 0.5 if we were writing it in decimals. The next problem, 15.7, says the value of the equilibrium constant for the reaction is, and then it gives us a number, 1.26 times 10 to the negative 12. And it says calculate the value of K prime for this reaction. And if you notice, this reaction is the reverse of the reaction above, and then it's also multiplied by 1/2. So you need to take the inverse of it, so 1 over 1.26 e to the negative 12th. And then, since it's multiplied by 1/2, you also need to raise this to the 1/2 power. And raising this to the 1/2 power, then I believe ends up being K equal to 890,870. Check my math on that, but I think that's pretty close. 15.8, then notice here's our K. K is equal to 5. But then notice the reaction and how it changes. It doubles here, it doubles here, and it doubles here. So since you multiplied this reaction by 2, you need to take 5 and raise it to that power. So it would be 5 squared. So K prime, that's what this should say, K of the new reaction is equal to 25. Number 16, for the endothermic reaction, remember when it's endothermic, you need to add heat to the reactants side. It says positive delta H right here. Le Chatelier's principle predicts that blank results in an increase in concentration of reactants. So we want to increase the concentration of these guys right here. So if we lower the temperature, then what it's doing is we're removing some of this heat. And if you remove some heat or remove a reactant, the reaction will shift in that direction. And so decreasing the temperature would cause it to shift to the left. For the gas phase reaction, which will result in an increase in the amount or concentration of the products, so we want to increase this, we want that to go up. And so in this case, what we want to do is shift the reaction to the right. And so shifting the reaction to the right would occur if you increase the concentration or amount of one of the reactants. And so it says adding N2 gas right here, which is letter D. And then number 18, which of the following equilibria will shift to the left towards more moles of gaseous reactants in response to increasing volume of a container. Remember, if you increase the volume, you decrease the pressure, and if you decrease the pressure, you'll shift to the side with the most moles of gas. So a decrease in pressure would cause it to shift this direction where we want it to, and it will shift there only if the reactants are the ones with the more moles of gas. And so if you look here, we have 3 moles of gas on this side, and here we have 2 moles, so more moles is actually on this side. And then if you look here, we have a gas and a solid, and here we have a gas and a solid, so that won't change. 1 gas or 1 gas. Here we have 2 moles of gas here. Here we have 3 moles of gas over here. 2 moles of solid over here, 4 moles of solid, and here we have 3 moles of gas. So the only gas in here is on the reactant side. So letter C would shift to the side with the most moles of gas. And there's only 3 moles of gas on the left-hand side. There's no moles of gas over here, so that is definitely the area where there's moles. And then just disproving the other ones, 2 moles of gas here, 2 here, and then 2 moles of gas right here, and 2 moles of gas right here makes it even. So C is our best answer. These will start in the next.